Once again, hey everyone, welcome back to the Expert Funda, and where we break down complex algorithm and make them easy to understand, right? So in this video, we will be driving into the Bellman-Ford algorithms, right? So as you can see here, right? So I have created a class Bellman-Ford, and then we will implement the code here. Okay, so we are driving into the Bellman-Ford algorithm, a powerful tool you can say in the world of graph algorithm, and it helps you to find the shortest paths from the single source from single source node you can say to all other nodes, right? So it means I want to say it will help you to find the shortest path from you can say a single source, right, to you can say to all other nodes in the weighted graph, right? Let's suppose this is your source, there will be multiple nodes will be there, right, or vertices you can say. And if this is your source and this is your target, right, so you can say we have to find the shortest path from a source, right, single source, to all other nodes. If there is multiple nodes are there, then and then if there should be a given weight, right? So weighted graph is having the you can say vertices as well as weight. Let's suppose like this. Okay, so there should be some weight is given, right? And so whether you are preparing for a coding interview or working in school project or just brushing off on your algorithm skills, right, for the interview, so this video is for you. By the end of this video, right, you will not only understand how Bellman-Ford algorithm works, but also how to implement it efficiently, that we'll see in the Java, right? So Bellman-Ford algorithm. So first question you should come in the mind is, what is Bellman-Ford algorithm, right? So the first thing first, we have to understand this concept, right? So what exactly the Bellman-Ford algorithm is, right? And unlikely Dijkstra algorithm, which also finds the shortest path, you can say, and the Bellman-Ford can handle graphs with a negative weight. But as you remember, yesterday I talked about the Dijkstra algorithm, right? So Dijkstra algorithm will not work efficiently in the negative weight, right? But the Bellman-Ford will work on the negative. It will work. Okay, so if there is given negative weight in the on the edges, right, it will work, right? So that is why Bellman-Ford is it's you can say famous for its algorithm. Okay, so this feature or this makes it incredible useful in the real world scenario, like in networks, right? If you know the networking or networks, how networks work, right, so it will be easy to understand you, right? But let's suppose what is network. So the network is similar type of graph, right? So where data packets might have very delays. Let's suppose from a network point A and point B, like this, right? The data packet will go with some packet, let's suppose 40, like this. Okay, there can be no data is going from A to C, there can be a minus something, right, like that. So in the data point you can say, right? So so this feature will work, this algorithm will work in the network scenario like this. Okay, so that is why this makes it incredibly useful in the real world scenario, right? So like in the networking, and we have talked about how the data packet works and how it delays while transmitting the data from network 1 to network B, or network B to network C, like that, or any other 2 points of the network, right? Now give me 1 second. Already talk about the what is the Bellman-Ford algorithm and why it is used. So we have talked about because it will work with the negative weight edges, right? Now think a graph example with the positive and negative weights, right? So if a graph having positive and negative weight, let's suppose, right, if a graph has positive and negative weights, then how will it works, right? So this algorithm will works by repeatedly relaxing all the edges of the graph, right? Meaning it tries to shorten the path from the source, right, to any other node by considering the edges. If there is a edge, right, so it has to consider the edge, right? So after a maximum of b minus 1 iteration will do b minus I b minus 1 iteration we will do, and then where we can say v is the number of vertices, v is the number of vertices, right? So iteration, let's suppose iterations. Okay, so I'm saying after a maximum of max of how many iteration we can do, v minus 1, v is the number of vertices. Okay, so the algorithm, this algorithm will guarantees that the shortest path if there is no negative weight cycle, right? It will guarantee the shortest path if there is no negative weight cycle. Understood? Let's suppose how the cycle is there. So this is a you can say a cycle, right? 3 nodes we have, 3 vertices we have. If this minus 3, minus 2, minus 1 like this, so this is called negative weight cycle. So there should not be a negative weight cycle. If there is no negative weight cycle, right, then the Bellman-Ford will work. So as you remember, when we are talking about the Dijkstra algorithm, Dijkstra was not working properly on the negative weight, right, of the edge. Here the same case, there should not be a negative weight edges, right, weight cycle, right? So these are the key points that you have to understand when you are working on developing the programs, right? When you are writing the course, right? When you are reading the questions. So based on that, you have to see which algorithm will works. Like see, the shortest path algorithm is 3 to 4 algorithms are there, right? That we have talked yesterday. But you have to see, will it work with the Dijkstra? Will it work with the Bellman-Ford? Will it work with the any other, right? So we have to see that. Okay, now let's understand how does it works. Okay. Okay, let's understand how does it work, right? How does it works? Okay, so first of all, let's break down the steps of the Bellman-Ford algorithm. So if you'll talk about the steps, right, so I'll go with the first step, right? Initialization, we can say. First we'll do initialization, right? So by what we will do, we'll start by setting the distance to the source node as a 0. We'll take a source node as a 0. Let's suppose if this is a source, right? So this node having a 0 weight. Okay, let's suppose this is 0. Okay, so we will start the source, we will start the distance, we will set the distance to the source node as a 0, and all other nodes as infinity. We'll define as an infinity weight like this. Okay, got it? Initially we will do that. First this having 0 and all others have a distance as a you can say infinity. Second we'll do you can say relaxation. What is the meaning of relaxation? So for each vertex, like for each vertex here, we'll apply relaxation steps to all edges. Means if the distance to a vertex can be shortened by taking an edge, we will update the distance, right? What I'm saying, if the distance to a vertex can be shortened by an edge, right? If we'll reduce one edge, then we will update the distance. Third, what we will do, third step, negative weight cycle detection will do, because Bellman-Ford will not work properly, right? Negative weight cycle detection. Let's write the detection also. Okay, so 3 steps will go. We will go with the 3 steps. First will the initialization. We will initialize the source node as a 0 and all other nodes distance is a infinity like this. Then in the second step we'll do the relaxation, where if the distance to a vertex can be shortened, means we will do sort by taking an edge. It will take an edge, right? So we'll take an edge and we'll sort a vertices, right? Then what we will do, we'll update the distance. Third, we have to find the negative weight cycle detection, right? Like let's suppose like when we are doing v minus 1 iteration, right? So after v minus 1 iterations, right? After v minus 1 iterations, right? If you can still relax any edge, right? If you can still relax an edge, it means there is negative weight cycle in the graph, right? If we have done, how many vertices we have? Number of vertices v, right? So if we are doing v minus 1, means we have completed almost all the node, right? So if you can still relax any edge, you have any edge, it means there is a negative weight cycle. How are we talking about? Let's suppose we have a cycle like this, okay? How many nodes we have? So in the first iteration we'll go here, then here, then still if you seeing that how many nodes are there? 3 minus 1. So how many iterations we have done already? 2. So we have completed 1 and this means still 1 have. If still 1 have, means this is a cycle, right? And then we can say we found the negative weight cycle. It's all have negative weight cycle, and so we in that case we have to relax that there is an edge left, right? Now, all right, let's dive into the code. We will start by defining our graph, right? So we'll start by defining our graph structure using a simple edge class, and then we will create an array of distance to keep track of the shortest path, right? Shortest paths, you can say. So let's begin. So we are going to write the edge class that holds the source and destination, right? So there we do not have any edge classes, so either we'll start here or here. I'll go with the here. I'll take a class and that is called edge, right? So this edge class will contain what? Sorry. So this edge class will contain what? First thing, the source, right? What is the source? Okay. Then we can take what? You can say destination. The data type is destination. Data type is same, so we are not creating in the next row. We can take a weight also. 3 things: source, destination, and weight, right? So when we are going to create the you can say edge, we need source, destination, and weight. So let me go to the source, then I'll go to the using the fields, select all, and we will create a constructor. Let me remove the super, not required. Okay, so we have created a constructor. This constructor will take a 3 things. It will take 3 things: source, destination, and weight. Got it? And it will initialize the object, right? So we have created the edge class, and it will hold source, destination, weight of each edges, right? Now now let's understand, let's implement the Bellman-Ford function, and that will initialize the distance and distance array, we can say, and relax all the edges, and finally we'll check for any negative weight cycle is there or not, right? So I'll create a function here in this class. I can remove this one later. We'll use later. Okay, here, or we can keep also the main class, no problem, no main function. So I'll take a function initially. Let's suppose we'll take void, right? And I'll say Bellman, and function name Bellman-Ford, right? And then in the Bellman-Ford we'll pass all the edges, right? So I'll take a list of edges, right? Not edge, it's edges, and then we'll take you can say source, not vertex, number of vertex v. Let's suppose v I will give, and source, we can take source also. Three things will pass like this. Okay. Okay. So we have taken Bellman-Ford function name, then we are passing the list of edges, number of vertices and source, right? Three things we will pass. So first of all, we'll create a distance array, dist equal to new and int, and we'll pass, this is array number of vertices. Then in this distance array we should fill some infinite value, right? Because that source should be, you can say source value should be 0, but all the value should be infinite. So we can take a max integer value and we'll fill all the you can say edges. So how we are going to do? There is arrays, as you remember study we have done, right? So arrays, then we'll do fill and we'll pass two things, the distance and another the infinite thing. So what is infinite here? In the integer we'll take integer dot max value, right? That we are talking about, right? What I was talking about, I was talking about when we are going to we are going to set the initialization, right? While doing the initialization, right, we'll start by setting the distance to the source node as a 0 and all other nodes as a infinity, and that is why we have taken integer dot max value here. Okay. Now think what we should do. So source we have not defined. You can write source at dist at source. Dist at source should be 0. So this is the initialization part, the first step we have done. So in the first step we'll do what? We'll fill the source as a 0 and all other edges distance will fill as a infinite value. So infinite value we have in the integer dot max value, and then the first step initialization is completed. In the next step what we will do, we'll go with the for loop, right? The relaxation thing that we have talked, right? So in the second step we will do the relaxation. So in this relaxation for each vertex, means for each vertex we have to go with the for loop, then we'll apply the relaxation steps to all the edges. Means if the distance to a vertex can be shortened by taking an edge, we will update the distance, right? So how we are going to do? Let's go. First we'll take int I equal to 1, then I should be less than vertex, right, and I plus plus, right? So we are going with all the vertices, right? Now for all the vertices there are some edges, right? We'll go with all the edges. Let's suppose we'll get one edge at a time, that is called edge from the edges, right? Like this we can make this sorry. So what I was doing here, so we can we have first of all we have traversed all the vertices. For all the vertices individually we'll go with all the edges, right? And so now we'll check if the distance at you can say edge dot source, what happened, dot source, why it is not coming? Yeah, distance dot source not equal to distance at what? Edge dot destination, right? If the distance is and the source is not equal, means we are not in the loop, right? Or what we should do, let me remove from it. So the distance at source, distance at is dot source, right? If it is not equal to infinite value, first of all we should take, right, integer dot max value, right? Means we want to check it should not be the infinite value, and then we will check let's suppose distance at what edge dot source plus we will update the weight s dot weight, right? If it is less than the destination, right? Let me, or what we can do after this, I will do like this, okay? And then I was talking about like this. So what I'm trying to say, we will traverse with all the vertices. For all the vertices, we'll go with all the edges. We'll check distance at source is, right, not equal to infinite if the source is not infinite value, and distance source sorry then we'll first of all we'll go with the vertices, then all the edges. We'll check the distance at edge source, if what is the source is having, right, if it is not max value. Then we will also check with the weight, we will add the weight and we will update the weight, and then we'll check if it is less than destination. Three things we'll do, and then we'll check if it is condition will match, then dist at s we will provide what, the source one, this one, we'll update it, we will update like this. Got my point? And then complete, no, we'll go with the complete this, we have to update the its weight also, right, like this. So what we are doing actually here, we will go with all the vertices, then all the edges, and if the distance not equal to the infinite value, the edge of source distance is not equal to the max value, after adding the weight, edge weight, if it is less than the destination, means destination edge should be updated with the source plus its weight, right? Like that we have to do, okay? And to test that, what we have to do, we can create a list of edges, provide the number of vertices and source, right? And you can run the for loop, right? You can do that, okay? So I can create here, let's suppose I will talking about the main, right? So in the main, what we can do, these edges we have to create, array list, we can take array list like this, and then number of vertices p is, let's suppose 5, and int source is 1, and sysout, rather than sysout we can pass the Bellman-Ford directly here, and we can pass all these three as vertex and source, and here we will make static without the object, we can call, right, like this. So to print the values, right, what you can do from the distance, right, here you can make a for loop here, and you can print here in the after this here, right? Or if you want to return this distance, what you can do, take it like this, remove the void and return the distance. Once for loop is completed, right, we can create a for loop, and the sys out will do test at what, I, right? But to do that you have to also create the edges, right? You have to, in the s, you have to write like s dot add, when you're going to new as like this. So first of all, what you will pass, you can see as the source, destination and weight. Let's suppose this is your source, this is your destination, and this is your weight. I will take all the weight as a similar values, you can say. Let me write this. Okay, okay, so I'll take 1 2 3 4 5. okay, the rest is not required, you can take if you want. And then I will go with 3 4 5 1. In middle I will take 2, its weight, I'm changing the weight, -3 and 2. Now let's run. What happened? Index is 5. okay, so welcome back guys. So what I have done actually, so I have renamed the vertices that we have created, right, like this, because it was the vertex issue, because we have to start from 0, right? So let's change the vertices with the 0. So I have started with the 0, then 1 2 3 and 4, and then number of vertices was 5. Source we have started with the 0, because we have to adjust the source that will match the 0 index vertices, right? Then we will start with the you can say distance. We will get the distance, right? We will not change the code, as you can see here, right? We have taken what we have initialized the things, right, like this. Then for all the vertices, we'll go with all the edges. We'll check if the source is not equal to the max value, if distance is less than distance plus its weight is less than the destination. Source and destination will check with adding the weight, and then if it is it will work, right, if the condition will work, then we will update the destination distance. Then we have to check the negative weight cycle, right? This is optional actually. If this is the case, right, all the edges, we can print graph contains negative weight cycle, and will return empty you can say array distance, right? And you already have seen the edges, right? So in this case we have just updated all these nodes, we can say vertices, right? And we'll create the for loop, and we will adjust the loop to iterate all the vertices, right? Let's print this distance from the source to the vertex for all the distance, right? You can see here, right, the distance from the source to vertex 0 is 0, source to vertex 1 is 1, source to vertex 2 is 3, source to vertex 3 is 0, source to vertex 4 is what 1, because in this it came 3, right? So till 2 we had what 3, now at vertex 3 it's -3, so it will adjust to 0, and then the next we have 1, so it will come 1 here. Okay, thank you guys, thank you for watching this video. I hope you like this video, the Bellman-Ford algorithms, right? And that's it. This code checks the shortest path from the you can say source to all the other nodes or the other vertices, and even detects negative cycle, negative weight cycle, as you can see here, right? We have created, right? But this is optional. Okay, and so that's we are going to wrap for today video. I hope you now have the solid understanding of the Bellman-Ford algorithm and how to implement it in Java. If you found this video helpful, please give it thumbs up, subscribe to Expert Funda for more content like this, and hit the bell icon to get notified when we post new videos, right? So also, if you can have any questions or topics you would like to cover, right, drop them in the comment below. And thanks for watching, and I'll see you in the next one.
Thank you guys, thank you for watching this video, and if you really like this video, please subscribe this channel.